We're now ready to take a look at an example of RSA encryption. This process does take a little bit of time, but it utilizes all of the tools that we have gathered so far. So first of all, let's go ahead and start with a message, and let's just say that our message P is going to be 8. Now, one thing I want to also point out is that here we're using capital P to denote the plain text, and lowercase p denotes one of our primes. So step two, we've accomplished step 1. We started off with numerical value. Let's go ahead and pick for our little p, our first prime, let's pick 5, and let's pick q equals 11. Now it doesn't really matter whether p is 11, q is 5. We only use these to compute n and b, so order of multiplication is not going to make a difference. So our value of n is going to be 5 times 11, which is 55. And our value of b is going to be 5 minus 1 times 11 minus 1, which is equal to 50. Excuse me, not 50, but 40. Next, we want to find a positive integer e such that the greatest common divisor between e and our value of b, which is 40, is equal to 1. So there are many ways to do this. One way in which to do this is just to pick a prime factor or a prime number, that is not a prime factor of 40. So we'll go ahead and choose 7, and so we want this GCD to be 1. So we'll choose e equals 7. So small enough for us to be able to work with on a small scale. Okay, so far so good. Our next task is to conduct the modular exponentiation process. So to find the ciphertext, our ciphertext is going to be congruent to our p value, which we chose our message to be 8, raised to the value of e, which we found to be 7, and mod n, well, n is equal to 55. Okay, so the modular exponentiation process, as usual, is going to be first of all to compute 8 mod 55. And 8 divided by 55 is 0, remainder 8. So that's congruent to 8. Next, compute 8 for 8 squared, and I'll just write this off to the side here. 8 squared is going to be 8 times 8 mod 55. And that's going to be congruent to the remainder of 8 mod 55, which is 8. So this is going to look the same just because the remainders are the actual dividends in this particular step. So nothing's changed here. So we basically have to figure out what's the remainder of 64 divided by 55, which is 9. Okay, so in our next step, we want to work our way up to 8 to the 4th. And I forgot to mention that 8 to the 7th, in terms of our binary values, 1, 2, 4, we don't want to go up to 8 to a power of 8 because that exceeds our current power of 7. So how could we sum up values from 1, 2, and 4 to get 7? Well, we could take 4 plus 2 plus 1. So we're going to compute this by collecting 8 to the 4th times 8 squared times 8 to the 1st. So this is going to be our final step in this modular exponentiation process. So 8 to the 4th is 8 squared times 8 squared mod 55. And that's congruent to the remainder of 8 squared mod 55, which is 9 times 9 mod, I wrote a couple of extra mods here. I'll go ahead and delete that one. Mod 55. And so 9 times 9 is 81, and 55 goes into 81 one time, and that's going to leave a remainder of 26. And that's it. There's our ciphertext value, is in this case, this is where we can stop and we can now compute our ciphertext value. So we wanted to find the remainder of 8 to the 7th mod 55, which we're going to write as 8 to the 4th times 8 squared times 8 to the 1st mod 55. And I should say that this is actually equal to, since all we're doing is expanding that value out. And even with 3 factors, we can sort of double up on that idea that if we multiply a bunch of factors mod 55, then we can take each of the remainders of those factors mod 55 and multiply them together. So 8 to the 4th is 26. 8 squared, its remainder is 9. 8 to the 1st, its remainder is 8. And we want to conduct this mod 55. And this is a fairly small value. I'll just put this into my calculator. 26 times 9 times 8, which is 1,872, fairly small number, divided by 55, goes into 1872 34 times. So 1872 minus 34 times 55 gives me a remainder of 2. So this is congruent to a remainder of 2. Now, what we've just done is just calculated 8 to the 7th mod 55, and so that's our ciphertext value. So what we have here is that our ciphertext value is 2. So in this case, we've gone from as a recap here, we started off with a plain text value of 8 and just computed the corresponding ciphertext of 2. So if Ann and Bill were communicating and Ann was going to send the digit 8 to Bill, then she would first encrypt it into a value of 2, send it off to Bill, and now Bill has to figure out how to undo this process so he can figure out what Ann's original message was. So the deciphering process requires 2 steps, a modular exponentiation step, which is the last one, but first of all, we have to find a value of d such that e times d is congruent to 1 mod b. And just to recap on this, this means that ed minus 1 divided by b is some integer, which I'll call k. That's some integer. And if I rewrite this whole thing, I can get d times e minus k times b is equal to 1. And what I'm going to do here is this negative, I'm going to relabel this integer, because if k is an integer, then the negative of it is also just the integer, but on the other side of 0 on the number line. So I'm going to call this t. So d times e plus t times b equals 1. Now this all has to do with the fact that the GCD between e and b is 1. That's why this step is critical. But more importantly, what I know here is that the GCD between these two values is 1. So I'm going to run the Euclidean algorithm so that I can then run the extended Euclidean algorithm to get the value of d. And I don't really care about the value of t, but I'm going to get it in the process anyway. Okay, so here we go. So we know that the GCD between e and b is 1. Okay, so that means the GCD between our value of e, which was 7, and our value of b, which I've already forgotten. Let's go ahead and scroll up and find that. Our value of b was 40. And I know that the GCD between those is 1. Okay, so running the Euclidean algorithm, we need to figure out how many multiples of 7 there are in 40, and there are 5 of those. So I'll just go ahead and box in our 2 values like so, and that leaves a remainder of 5. Now the remainder between 40 and 7 is the same as the remainder between 7 and 5, so I'll go ahead and carry those down as my new values. And so we'll have 7 is equal to some number of multiples of 5, and 5 goes into 7 one time, leaves a remainder of 2. Now, again, I know that the GCD between 7 and 5 is the same as between 5 and 2, so I'll carry 5 down to the next line and figure out how many multiples of 2 go into it. And I know that 2 multiples of 2 go into 5, leaves a remainder of 1. My final step is that now I'll see that 1 goes into 2 times, leaves a remainder of 0. And so at this point, we would be able to conclude that that's our GCD. That's our GCD right there. And so at this point, we're going to back up. We're going to start from here and execute the extended Euclidean algorithm. So what I do in this first step is I rewrite in this equation right here, I'm going to rewrite that in terms of 1. So 1 is equal to 5 minus 2 times 2. Now what I'm keeping track of, the reason I box these in is for 2 reasons: to see what's been carried down to the next line, but also because I want to make sure that when I make a substitution, that in my next substitution I'm going to replace 2 with 7 minus 1 times 5, and I want to keep track of the 7 and the 5s. So I don't want to multiply those things together. Okay, so that means that 1 is equal to 5 minus 2 times this 2 here. That's going to come from this step. And so 2 is equal to 7 minus 1 times 5. Now I'll go ahead and expand that out. That's 5 minus 2 times 7 plus 2 times 5. And again, what I'm trying to keep track of in the substitution is the 7 and the 5. So 1 is equal to, I have 3 5s and I have negative 2 7s. So that's 15 minus 14, which is still 1. Now in my final substitution here, I'm going to replace 5 in terms of 40 and 7. So we will now take 1 equals 3 times 5. So 5 is 40 minus 5 times 7. And I guess what I want to do here is emphasize that we're making that substitution. And so I'll go ahead and do that in this color. So let's pick black. Okay, so in this step here, I'm replacing 5 with 40 minus 5 times 7. And then, of course, I have my minus 2 times 7 over here. And this is my last step, so I'll just expand. I have 3 times 40 minus 15 times 7 minus 2 times 7. And I'll just collect my terms. I have 3 times 40 minus 17 times 7. All right, well that now has the form that I was looking for. Almost, let me rearrange this a little bit more. My value of E is 7, so I have negative 17 times 7 plus 3 times 40. And I'll just go ahead and make the note here that according to this equation, this would be the value of D. This is my value of E. This is my value of what we're calling T, which is not going to be used at all, but which inadvertently gets calculated. And this is my value of B. Now we've got one problem here, and this is a fairly straightforward problem to resolve. My problem in this line is that D is negative 17, but D must be non-negative. Oh boy, well, this is not a unique equation, fortunately. There is a way to undo this, and here's the algebraic trick. So my trick is, if D is negative, add and subtract E times B from the right-hand side. And that might seem like a really strange thing to do, but let's see why this is going to work. So I'm going to add 40 times 7. This is B times E, but 7 times 40 and 40 times 7 are the same. And I'm going to also subtract that, but I'm going to subtract it as 7 times 40. So you can see that this difference right here is 0. How could it possibly help me make D positive by adding 0? Well, if we look at like terms, and this is just sort of a cool little number theory trick, if we see that we have 40 sevens here, and then we have negative 17 sevens here, then really we have 33 sevens. And also, if we have 3 40s here, and then we have negative 7 40s here, then that just means we have negative 4 40s. Alrighty, we're almost done. So if we do that, we said negative 17 sevens plus 40 sevens gives me 23 sevens, and 3 40s minus 7 40s gives me negative 4 40s. And so now this is still of that correct form. This is my value of D, because this is my value of E. This is my value of T, which again, I don't care about that, so that value of T can be negative or positive, makes no difference. And this value here is still B. So just to see that this works out, I'll go ahead and punch into my calculator 23 times 7 minus 4 times 40, and that still equals 1. Why does it still equal 1? Because we added 0 to both sides, or to the right side. And so my conclusion is that D is equal to 23. That's the smallest possible value of D that I could have. Now let's conduct the last step, and this is just our normal ritual of performing modular exponentiation. So now Bill is wanting to obtain that plaintext value, so he knows he needs to compute the ciphertext, which, if we recall, was equal to 2. He needs to compute 2 to the 23rd mod n, which was 55. All right, so 23 is not a binary value, so let's just write out a few. So 1, 2, 4, can keep going, 8, keep going, 16, 32. Oh, wait, that's too big. So I know that 23 is going to be 16. Can't add 8 to it, that'll give me 24. Plus 4 will give me 20. Plus 2 will give me 22. Plus 1 will give me 23. So I'm going to rewrite 2 to the 23rd as 2 to the 16th times 2 to the 4th times 2 squared times 2 to the 1st, and compute that mod 55. So this just requires a few steps. Again, it's kind of a long process, but now we can kind of see why all these tools were valuable. Hopefully we get the right plaintext. So here we go. We know that 2 mod 55 leaves a remainder of 2. Now we're going to do 2 squared, which is 2 times 2 mod 55. So the remainder of 2 mod 55 from the previous step is 2. So we have 2 times 2 mod 55. Sometimes this happens if your divisor is really, really large and it takes a while for the exponentiation to grow past 55 to see how this pans out. Okay, so here we go. 2 times 2 mod 55 is 4 mod 55, which leaves a remainder of 4. Now 2 to the 4th is going to be 2 squared times 2 squared mod 55, which is congruent to the remainder. Oh goodness, well that's still just 4 times 4 mod 55. And that's 16 mod 55. 55 doesn't go into 16, but leaves a remainder of 16. And we have a couple more steps. Now we're going to do 2 to the 8th, which is 2 to the 4th times 2 to the 4th mod 55, which is congruent to the remainder of 2 to the 4th, which is 16 times 16 mod 55. And I think we're in motion here. 16 times 16 is 256, and 55 goes into 256 4 times, leaving me with a remainder of 36. Okay, great, and that's now a valid remainder. So now we move on to 2 to the 16th, which is 2 to the 8th times 2 to the 8th mod 55. And okay, that's congruent to the remainder of 2 to the 8th mod 55, which is 36 times 36 mod 55. And 36 times 36 is 1,296. And that divided by 55, so 55 goes into 1,296 23 times, so I'll do 1,296 minus 23 times 55, which gives me a remainder of 31. All right, here we go. So now we can construct this. This is congruent to 2 to the 16th, which has a 2 to the 16th mod 55. That's 31. 2 to the 4th mod 55 is 16. 2 squared mod 55 is 4. And 2 to the 1st mod 55 is 2. And so we need to compute this mod 55 because 31 times 16 is already going to give us a big value bigger than 55. So 31 times 16 times 4 times 2 gives me 3,968 mod 55. And 3,968 divided by 55 gives me 72 and some change. So we'll take 3,968 minus 72 times 55, which gives me, lo and behold, it gives me 8. And that is our final computation. That right there is our original plaintext value. So, yay, we did it. Now you can see one of the purposes of doing this whole process and why we're doing this by hand is to see how difficult it already is for the human brain to be able to process all of this. So when a computer is dealing with really, really large numbers, without these different tools that we've established, the modular exponentiation, Euclidean algorithm, extended Euclidean algorithm, there would really be no efficient way to do these computations.